Okay, this third try on recording this video. Yay for me, huh? Hey, welcome. Section 6.5. This has two pieces of information. One is about the trapezoidal rule, so approximating using trapezoids. Not new to us, right? We've done this one before. And then the other one is Simpsons rule, which is new to us and has a formula that expresses another way to calculate the area under a curve. Looking at this, just a little repeat on trapezoidal approximations. I see some trapezoids going on here. Let's look at trapezoid 1. Trapezoid 1 has a left height and a right height, and of course a width that we call delta x, right? Then I go on to trapezoid 2. Trapezoid 2 has a left width and a right width, or height. What am I saying? Width. Those are heights. And then, of course, it has its width of delta x, whatever that might be. I go on to trapezoid number 3, which is going to be calculated kind of funky here. It's going to have a left width, or height, I should say, and a right height. And trapezoid 4, you're getting kind of bored with this, right? Here's our delta x. It has a height on the left and then a height on the right that I would need to sum together and go 1/2 height on the left plus height on the right. What you should observe off of this is the fact that, look at these, they got doubled, right? Every interior height gets used once on the right, height on the right, and then it gets used again in the next trapezoid as a height from the left. This would be the height on the right, and then it gets used again as a height on the left. The very first one is a height on the left, never utilized more than once. And then I finish with a height on the right, and it only gets utilized once as well. Well, knowing that, it allows us to create a fast formula for trapezoidal. So if you don't like doing trapezoids one by one by one, there is a fast method. The fast method has one restriction though. You must have equal partitions. So delta x must be equal subintervals. If that's the case, you can use this faster method, as we'll walk through below. But the one thing, it must have equal subintervals. The reason being is we're going to GCF that delta x from each and every trapezoid that we encounter. We're going to take and factor that forward. So here's my delta x, isn't it? B minus a over n, which would be equal subintervals. The 1/2 from the formula is right here. So both of those items get factored forward as a GCF. Then you'll notice we have one height on the left, a sub 0. So it's our function evaluated at the x value a sub 0. Then I get double of the height evaluated at a sub 1, because we had a left and a right that would get, utilized when doing a trapezoidal calculation. 2 of the next one, a sub 2. All of these interior heights get utilized twice, and you'll see the 2, 2, 2 pattern continuing on and on until I finish. And then my end units only have a 1 coefficient. So there's a quick method for trapezoidal if you have equal subintervals. The other thing interesting to note that we've talked about before is that I could calculate my left rectangular approximation, and I could calculate my right rectangular approximation, add the two values together, divide by 2, and that will turn out to be a trapezoid. All right, we're not going to do this one. If you wanted to, you could walk through this problem at the bottom of the page and see where that takes you. You're calculating the area under the curve of of the integral 1 to 7 f of x, so under the curve of f of x. I think it's a good idea to always start off with this is approximated and use your approximation symbol, and then go into your 1/2, delta x. Does delta x stay consistent here? Oh, no, it doesn't, does it? So we would have to individually work on the trapezoidal area calculation and move on to the next one and do left and right on that. So if you want to practice that one, see what you get for an answer. 160 is the answer. Okay? All right, I'm going to keep moving forward till we hit the Simpsons rule. Simpsons rule. Let's read the paragraph, and it says Simpsons rule divides the interval into even number of subintervals. That's important. Highlight that, underline that, do something with that. And on each pair of those subintervals, it approximates the area under the curve using a parabola on the top. This produces a much better approximation than a trapezoidal rule. So if I had a multiple choice question asking whether Simpsons or trapezoidal is best, typically it says it often produces. Typically Simpsons rule is going to be more accurate than a trapezoidal, and trapezoidal is more accurate than a midpoint, and midpoint is more accurate than a left or a right. So just kind of hierarchy there. Okay, let's take a look at Simpsons rule. You can see it laid out here. Maybe you can make sense of it. It says take delta x and divide it by 3. I often think of Simpsons as 1/3 times delta x, and then I go into my pattern. We know delta x. Delta x is calculated as the endpoints subtracted, so b minus a over n. And it has to have even number of subintervals. Then the thing that I want you to pay attention to is look at how this pattern goes. There's a 4, a 1, a 4, a 2, a 4, dot, 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 dot. So 4, 2, 4, 2, 4, 2, 4, 2, and then I end up with 2, 4, 1. You should always have a 4 prior to the 1, and I should always have a 4 following the 1. So it starts off with 4 and it will end with 4. These are all the interior heights. The exterior heights only get 1 and 1 as a multiplier. So note you must have an even number of subintervals. We've said that a lot, haven't we? And it uses parabolas as it approximates the area under the curve. Here's a quick sketch of an idea. In the black, you can see that I've got trapezoids built, and then you can see the red curve. And then so notice that each approximation actually covers 2 of the subintervals, and then we get this 1, 4, 1 calculation going on here. So it's utilizing 3 points in its calculation, which kind of creates this parabola. That's probably a little extreme, isn't it? It probably would go something like that. But yeah, so parabolas will be more accurate. And if you want to delve into this a little bit more, you can kind of look at this diagram here where it's calculating out the parabola shape on top and calculating some area. It's very involved, the calculations going on, and you don't have to know the theories behind that, but if you're interested, go do a Google on it. All right, the drawing below, let's go through this. This was an AP question once upon a time. The drawing below represents a parcel of property running along the jagged side of the river. So here's our river, right? The jagged side. The owner measures at each 10 meters intervals and gets the length of the property from that straight edge to the river's edge. And you can see the numbers in the diagram. All right. Using the measurements as recorded, approximate the area of the property using, we're going to do 3 different ones. I'm going to do a Simpsons with 4 subintervals, and then we're going to do a Simpsons with 8. So since this is even, that allows us to do Simpsons. I need to calculate out my delta x. My delta x would be the distance between our endpoints, 80 minus 0 divided by 4. So I'm getting a 20. And so I'm going to be blocking here. And then my next calculation will be there. My next calculation would be there. And our final calculation will be there. So we get 4 of them, right? And area using Simpsons, we'll do area sub S, is going to be 1/3 delta x multiplied by 1 of the first heights. So this would be evaluated at 0. Then I go into a 4 pattern. That would be our next height at 20. And the next one will be calculated at 40. Now I switch to 2 of f of 40. I need to extend down here, plus back to 4, because those alternate between 4 and 2, 4 and 2. And then finally, we're at our very end, and that only gets a 1 evaluation at 80. So what did we do? We had a 1, a 4 times that, a 2, a 4, and a 1. And that's going to give me a 1/3. Delta x is 20. And then I'd have a 1 times 60, that meant to be a parenthesis, 1 times 65, a 4 times 47, a 2 times 51, a 4 times 31, and a 1 times 80. Oh, 43. 43 was its height. And then I could get all of that put together. I'm sorry, I put my paper away. I don't have the actual area right now, but we're going to grab it, so leave a spot for it. We'll go fill this box in a minute. Let's do Simpsons with 8. See if you can do the setup. Hit pause, see if you can do it. Calculate out your delta x. This time, difference between our endpoints divided by 8 equal intervals will mean 10. So I'm going to go a 1, 4, 2, 4, 2, 4, 2, 4, 1. I feel good because I ended up with the 4 before the 1 and I started with a 4. And you should always begin with 4, end with 4 after the 1s. All right, so my area for Simpsons, 1/3 delta x. 1 times the first height, 4 times the second height, 2 times the third height, 4 times the fourth height, 2 times the fifth height, I think, and then 4 times a 31, a 2 times a 31, a 4 times a 43, oopsie, and finally 1 times the last 43. And we can get an answer for that one. I'll fill that in a moment. That would be more accurate than the one with 4, wouldn't it? Than our previous one in A. Lastly, let's go do trapezoidal. And just as a means to compare, this one says with 8 subintervals. Ooh, 8 trapezoids does not sound like fun. But remember, we have equal subintervals. So for that, I'm going to do the fast trap method. It's good to get an example of one of these too. So delta x we know is difference in our endpoints divided by 8. So we're going to have 10 as our common interval width. Area trap is a 1/2, not a 1/3, as in Simpsons. Delta x. And the formula went 1, 2, 2, 2, 2, 2, 2, 2, 1. So I'm going to have 1 of the first height, 2 of the second height, and so on. 2 of 45, 2 of 51, and then another 2 of 51. For the AP, oh, I'm sorry, it's a 31. I was looking from the side. A 2 at 50, another 2 at 31, a 2 at 43, and a 1 at 43. A little faster than setting up each and every trapezoid, right? And we can come in with an answer on this. Had I set up each and every trapezoid, it would have looked like my first trapezoid, height on the left, height on the right. Next trapezoid, and I'd have to do 8 of these. Height on the left, height on the right would have been a 58 and a 47. Third trapezoid, I'm not going to do many more, just so you know. Third trapezoid, I'd be joining, where am I at? This is my third trapezoid right here. This was trap 2 and this was trap 1. 47 and a 51. And this pattern would continue, wouldn't it? What do you notice out of this? Here's this fast method. I used a height on the left and a height on the right. Well, actually it's right, then left. Then I was, height on the right side was 58. Height on the left side, I'm sorry, left, right, this would have been height on the left, height on the right. And then height on the left, height on the right, utilizing 47 twice. And we've got those accounted for, those doublings of 58, 47, 51, and so forth. All right, answers. Let me hit pause, and I'm going to go look up these answers that I promised you, unless you've already done them. Okay, we got sums here. On the very first one, this came to 3480, 3580, and lastly, trapezoidal came in at 3600. Perfect. Okay, your homework is there is no Delta Math because that's a last year thing. You're basically just doing this AP worksheet and giving that a go. So have a good day. Bye-bye.